Thank you all for showing up this cold Saturday morning. So we'll be talking about rolling and bouncing. And so this is a project for, one of my projects with a few students. Tim, Chris, Boe, these are former students. Hong Kun was a long-term collaborator from UMass Amherst, and ZJ is a current PhD student of mine. And the hero of this story will be the Super Bowl, right? The Whammo Super Bowl. So I wonder, you may have seen this in the testing of the equipment here, but let's see if I can move. I wonder how many of you have seen this TV commercial.
Super Bowl! Look, it's almost alive. It bounces and bounces, keeps going and going almost forever. Hurry, try and catch it. Super Ball is a mystery ball of 1,000 bounces, with many more bounces than any ball you ever owned. It is a Super Ball. It zigs and it zags. Fast bounce, high bounce. The most amazing ball ever created by science. Energized Super Ball is now in your hands. With amazing rebound, Super Ball actually bounces over a house. Now, watch Super Ball carefully in slow motion. Strange, weird, makes every bounce a game. Every game more magical. And it's still bouncing. Hurry, discover your new power with Super Ball. Under $1 wherever toys are sold.
I've got my Super Ball!
By Whammo.
This is probably from the mid-60s, I would say. I wonder if this sound is recognizable to some of you. And what you'd see, if I could show the video, were a few cute experiments. It would show someone throwing the ball and that would go over a house. There'll be someone throwing the ball inside sort of a cubic room, and the ball would behave in some peculiar way. There are a few experiments that we're going to reproduce in the math. Yeah.
They would always break if you hit them too hard. You gonna explain that?
What's that?
They would break if you would hit them, bounce them too hard.
Well, here's the thing. The real ball, if you go to the Amazon and see the people who bought it, the reviews, some disgruntled buyers will complain that the actual ball will break. We are going, right, it will break in two hemispheres. We are going to be dealing with the ideal mathematical Super Bowl. They will never break in two.
They said it had 50,000 pounds of compressed energy too.
Well, they have a restitution coefficient from what I've seen of above 0.9. And the ideal Super Bowl, the mathematical Super Bowl, will have a restitution coefficient of 1. So let me, before I get to the definition of the ideal Super Bowl, let me point out this paper. How many of you know Richard Garwin, the very famous physicist? He died in 2025. And he's mostly known for his work on the design of the hydrogen bomb. But he was sufficiently intrigued by the behavior of the Super Bowl that it inspired him to write one paper. That's one paper I know by a famous physicist, probably his quirkiest paper, where he explains the phenomenon of, right, you throw the Super Bowl under a table, it will bounce against the floor, bounce against the underside of the table, and then come back, bounce again on the floor, and it gets back to you, right? We'll see this kind of behavior in ideal form. This is Richard Garwin. I'm very certain that he didn't win the Presidential Medal of Freedom for his work on the science of the Super Bowl. It was for something else. But here he is with the highest compliment a genius can give to the other. This by Enrico Fermi. So again, to reiterate the point, I guess it's a natural thing in physics or in most sciences that if you want to understand, right, to theorize about a phenomenon and develop, right, predictions that could be tested later, you don't want to deal with the full complications, right, of the system in kind of its most realistic description. You want to clean things up, simplify, make a mathematical model, and then you study the model, right? And that's what we are going to do. And so, as I said, we are not going to study the real Super Ball, but the ideal, right, Super Ball that lives in mathematical heaven, right, which all the real Super Balls can only aspire to be, right? The Platonic ideal of a Super Ball. That's what we need to first characterize, right? So I want to give first a definition, right, of the mathematical Super Ball, and that's what we are going to work with. So first, our Super Ball will be, a rigid sphere, right? Perfectly spherical and rigid. You may wonder if a perfectly rigid sphere can bounce, but I think it's a fine idealization. For example, if it's a beach ball, it bounces and deforms a lot, right? Maybe if it's a baseball, it's much more rigid. It bounces somewhat. If it's a bearing ball made of steel, well, it's pretty rigid. You're not going to be able to deform it with your fingers. It bounces. So we can imagine taking the limit, right, and to have a ball that only deforms infinitesimally, and it will be perfectly elastic, and that's the limit. And now to specify its behavior, right, we have to specify how it responds to impact, right? And so fundamentally, to characterize the mathematical Super Ball, we need to specify a function. It's the function that gives the post-collision velocities from the pre-collision velocities, right? What are the velocities? Well, you have the velocity of the center of the ball, called the linear velocities, right, or velocity components, and we have the spinning of the ball, right? So the angular velocities. So together, right, we have a set of parameters, and and we need to specify a function, right, that from velocities in will give us velocities out. It's this function, I'll call it a collision map, a map in the mathematical sense of a transformation or as a function, and sometimes I'll call it a billiard map for reasons that will become clear. Billiard dynamical systems, it's an area of mathematics, and I will explain a little bit its sources in physics. But this is our first task, right, to define this collision map, right? And let's list some of desirable properties, right, that would like it to have. So first, again, the ideal ball, I mean, the peculiar features of, one of the reasons for the peculiar features of the Super Ball is that it has very little dissipation, right? If a real ball, right, there will be some heat generated at the bounce. The sound that you hear, right, is energy that is being converted into sound waves. Well, the ideal Super Ball will just bounce all the energy that went into the impact is recovered in the rebound, right? So that's one first assumption. Another assumption is time reversibility. So the fundamental laws of mechanics are time reversible, right? What does it mean? If you record on a video, right, a movie, the event, right, the bouncing event, right, and then you run the movie backwards, what you see is physically, well, it is a process that will be described by the same map. In other words, it's a viable process, right? The idea of irreversibility, right? Typically, irreversibility has to do with more complex phenomena that have some kind of thermodynamical aspect to it, right? The fundamental laws, like basic laws of classical Newtonian mechanics, they are time reversible, right? So we'll make that assumption. Another assumption that is very natural is that in order for the ball to bounce, right, let's say against a rigid surface, the forces, right, there are impulsive forces that the wall is imparting against the ball, and those forces, so they happen, very intense forces for a short period of time, and those forces will be acting at the point of contact, a single point, and of course, once those forces are applied, they are distributed through the ball, and all the pieces of the ball will move together, right? Hopefully without splitting. So that's a very natural assumption. It's an idealized assumption because the actual ball will deform a little bit, the region of contact will flatten a little bit, right? The ball will be kissing the wall with, right, in a little disc, that flattened region of contact, right? And so the forces are acting on an small extended region, but the idealized ball, the forces act on that point of contact.
Does spin or angular momentum play a role? Spin or angular momentum?
Absolutely. But you'll see that coming up. That will be very central to the story. Right? A final assumption is linearity. So here, maybe this requires a little justification. It's a mathematical assumption. The idea, linearity means that the effects are proportional to the causes, right? So here, maybe to illustrate, I have my super ball here. I impart on the ball's initial conditions, initial velocities. Then I see the velocities after the collision. Then if I double the initial velocities, I double the post-collision velocities. It is not unreasonable. For a moment, I thought that I could prove linearity from the other assumptions, but I was told by my favorite large language model that in fact there are examples of nonlinear impact satisfying all the other conditions. I didn't understand the example yet, but it's quite possible that there may be, but they don't seem to be physically well motivated, so ignore them, right? Okay, so these are the assumptions we'd like to make. Here's a theorem. Under these assumptions, there are only two alternatives for the map. The first alternative is what I'll call the standard. It's standard because it's in the dynamical theory of billiards, in theory of dynamical systems, this is always assumed. And this means what? The situation can be interpreted physically as a ball which has a surface that is perfectly slippery. When it collides with another surface, there is no grip. It's simply the state of spinning is not affected. And so the rotation, the angular velocities do not change during any process, right, of a sequence of bounces. And by that, because of that, the system reduces to just observing the motion of the center of the ball, right? So in that case, what will happen is that when the ball hits a wall, it will reflect specularly. If you follow the trajectory of the center of mass, nothing happens. So linear and rotational motion are decoupled in that case, right? This is a purely slippery or the slip collision collision map, and it's widely studied. So if you Google, papers on billiard dynamical systems, all that you see is this sort of system. You have a region with a certain boundary. You have a point, a point particle that moves around in rectilinear uniform motion, hits the boundary, reflects specularly, right, like a light ray reflecting on a mirror, and that's it. The other case is going to be our model of the superball. We could call the rough collision map or the no-slip collision map. And in this case, indeed, the translational and rotational motions are strongly coupled. And so all the interesting effects will come from this, right? You can imagine that the surface of the ball is rubbery, right, in an ideal sense, so it engages with the surface that it impacts on, and it could initially come without any spin, and then it bounces. Part of the translational momentum is converted into rotation, right? This is the superball, that the mathematical Platonic superball that we're going to study, right?
Question?
Yeah.
So are you saying in number one there that if you've got spin on the ball and you throw it into a wall and you have situation number one, it won't affect the rebound at all?
The rotation will not affect the rebound, only the linear velocity. Yeah.
So the total energy is going to be the summation of the rotation plus translational. So in the first case, are you saying that the rotational energy doesn't change between pre-collision and post-collision?
Yeah, you have separate conservation laws for the two modes. So both the kinetic energy for the linear motion is conserved, and for the rotation is conserved.
But in the first case, I'm saying the rotational energy stays the same before and after the collision?
Absolutely.
Okay.
Not only that, but the state of rotation stays the same. The angular velocities don't change at all. And so that's why it's enough to understand the motion of the center of the ball, right? Another way to think about this case.
It could be ignored, couldn't it?
Absolutely, absolutely. And it is ignored. So in the literature on mathematical billiards, people don't even think about a ball or a disc. It's just the point particle that moves, right? You could also think that you have the ball, and by the way, I'm going to assume generally in the examples that I give that the mass distribution is uniform, right? But if all the mass, you can have a positive radius, but if all the mass is concentrated at the center, right? The same thing. It will behave, right? The moment of inertia is a parameter that couples the two things, and in that case, the moment of inertia will be zero, right? Okay, so let's see. Before we get to the superball, let's look a little bit at the standard case, because there is a long, interesting story about it that I'd like to tell you first. So here's an important physicist. I would call, okay, you may call him a physicist, I'll call him a mathematical physicist, Ludwig Boltzmann. And he had a dream, right, which was to establish mechanical foundations for thermodynamics, right? In particular, a difficult task of explaining irreversibility in thermodynamics, right? By the way, irreversibility, if a real ball, it will bounce with decaying amplitude, you dissipate energy. Dissipation is a thermodynamical process that implies irreversibility. Irreversibility has to do with the arrow of time, right? There is a direction that time goes. It was his goal, right? A dream is a poetic way to say that's what he wanted to establish. To a large degree, he established the the foundation. There were problems that he had to face because the math wasn't quite ready for his ambitious goal, right? So I'll call it a dream, but what he wanted to do is still a topic of research in mathematics. If you have heard of, optimal transportation theory, things that, there was a Fields medal a decade or so ago on the Boltzmann equation. It's a mathematical topic that is extremely important. He's the founding father of this line of investigation. But in something he needed a technical mathematical sort of assumption that was extremely hard to establish, and that is the notion of ergodicity, right? Ergodicity is an assumption that allows you to look at the space of states, microscopic states of the system, do a kind of averaging, and obtain something of thermodynamical significance, right? So this averaging operation he needed to do requires an assumption that is called ergodicity. I won't get into the details, but let me simply say that ergodicity, in the theory of dynamical systems, there is a hierarchy of mixing properties. Mixing in the sense that your dynamical system mixes points in the space of states, the phase space of the system, and the stronger this mixing, the more chaotic, right? To use a vague term, the more chaotic the system is. Ergodicity is the lowest rung in this hierarchy, right? It's a very mild form of chaotic behavior. It's the least that you need in order to apply some sort of law of large numbers, right, to your description of the physical system. Now, he was deeply criticized for his work at the time. You have to remember that end of 19th century, the very existence of atoms was not widely accepted, and the physics community was so steeped into the description of nature in terms of calculus, right, the continuum, that even the idea of atoms didn't quite fit so well with the way people theorized about physics. And there were other mathematical issues that it required development that came later. And so Boltzmann was very disillusioned with the response he got from the establishment of the physics community, and I understand he committed suicide in 1906, right? Although the younger generation coming after him was very supportive, right, very strongly behind him, but the old guard didn't receive his ideas well. We'll get back to that in a moment. So, and by the way, this Boltzmann's scientific signature, right, the equation S equals K log W, right? S is the thermodynamic entropy. This is, by the way, his tombstone, right? S is thermodynamic entropy. K is the famous Boltzmann constant. W is some measure of the number of microstates of the system that are compatible with some thermodynamic state. It's a famous key connection that he established in trying to make sense of statistical mechanics, right? Which is an area that he was one of the founding fathers of, together with Gibbs, right? Now, what happened after that was, so ergodicity was very, very hard to establish mathematically for realistic physical systems. So what happened was that the subject moved to mathematics. Pure mathematicians started thinking about it, and they started developing techniques for proving ergodicity for very, systems that had nothing to do with physics. Coming from number theory, coming from geometry, coming from algebra, combinatorics, and slowly techniques were developed that to that could be used, the tools, right, could be used to prove ergodicity for mildly realistic physical systems. Here are a few names. Poincaré will make an entrance in this story in just one slide or two. Von Neumann, Birkhoff, Koopman, Hopf, Kenshin. This is the old school of ergodic theory, right? And then around the time that Super Ball was introduced, but it wasn't at all in the minds of the Russian mathematicians. This is Yakov Sinai, a very important name in the development of the theory of chaotic dynamical systems, the Moscow State University School of Dynamical Systems. And he was the first to propose and prove ergodicity for an extremely simple model of something that you could vaguely call kinetic theory of gases, right? It's a gas in a square, right? In a box, two-dimensional, with two molecules, right? And even for that, it was a tour de force to prove ergodicity. But he introduced techniques. The proof, by the way, it was announced in '63. But there were gaps, mathematical gaps. It was a very complicated technical thing, and that created an industry for establishing ergodicity. And the main approach actually depends on something that, so what is called chaotic systems in the broad literature, in pure math would be called hyperbolicity, right? So the models that Sinai worked with, they were hyperbolic systems. Those are in the hierarchy of chaos, those are at the top, right? Much stronger mixing properties than simply ergodicity. And that was the beginning of the theory of chaotic dynamical systems. So generically, the systems, these I'll call Sinai-type billiard systems, are ergodic, they are chaotic very strongly, and it's the origin of the whole story. So the Russian school were main pioneers at beginning with Kolmogorov, the famous Kolmogorov, the father of modern probability theory. Until his work in the early 30s, probability theory had a peculiar status, right? Because there wasn't any axiomatization of it. He was the one who gave a solid mathematical foundation for probability theory, and that was essential for development of ergodic theory. So he worked in statistical mechanics, stochastic processes, complexity theory, was a major name in in mathematics and the theory of dynamical systems. Here, Boltzmann and Poincaré were in St. Louis in 1904. If you go to Holmes Lounge, there is a plaque about the meeting of engineers, right? So during the World Fair, there was the International Congress of Arts and Sciences. That was a time when Boltzmann wasn't really in good terms with the mathematical physics community, but there he is, 2 years before his death. Can you recognize him? He's the one with long beard sitting in the front row, right? As I said, he died in 1906, and there's a sad irony there because 1905, Brownian motion, Einstein, Smoluchowski, right? It was the foundation of the kind of theory that was needed to, and later empirical work by Jean Perrin, right? That finally puts to rest any doubts about the existence of atoms, right? So if he lived just a little longer, he'll feel strongly vindicated, right? But anyway, so I would like to mention Poincaré's presentation at the meeting. It's a fascinating read. The title you can easily find the paper online, The Present and Future of Mathematical Physics. 1904, right? 1 year later, Poincaré was very very knowledgeable of everything that was going on in the mathematical physics scene. And he was anticipating some developments, right, that came soon afterwards. Einstein, right, his Annus Mirabilis, right, 1905, Brownian motion, photoelectric effect, quantum theory, right, the equivalence of mass and energy, the famous E equals mc2, the Brownian motion, right, all came fairly, and Poincaré was anticipating this new physics coming up in the horizon. It's quite worthwhile a read. The paper has this title, The Present and the Future of Mathematical Physics. So let me tell you a little bit about Sinai's billiard. So this is a kind of a modification of the billiard. It started with a box, a square box in dimension 2 with two discs that can move, right, and collide with each other. After a mathematical transformation, you can represent the whole thing as a single point particle with a larger circular scatterer in the middle, and the collisions are specular. I'm still talking about the standard model. I didn't get to the super ball yet, right? So it's a deterministic system, but it's highly chaotic, which means that trajectory behavior is highly unstable. You cannot predict after a short period of time exactly what is the configuration of the system or the state. But exactly because it's very unstable, it lends itself very well to statistical analysis. And so that's the heart of the idea of chaos, right? You have a system that is deterministic, but you can use probabilistic techniques, probabilistic limit laws like law of large numbers, the central limit theorem, those kinds of things, to do a very detailed analysis, right? Probability is applied in a very fruitful way to a system that is purely deterministic. It has positive entropy. There are many different notions of entropy here. I'm talking about the Kolmogorov-Sinai entropy, which is a kind of measure of complexity of the system. Having positive entropy indicates that the structure of trajectories, right, in the phase space of the system can be very complex. And it's not only ergodic, that's Sinai's theorem, but it's highly mixing, highly chaotic, right? Keep this in mind. It will be in great contrast with the Super Bowl, right? Okay, so let's move on finally to the Super Bowl, right? The mathematical Super Bowl. So I'll do a few experiments, right? The first experiment is the following. Imagine I'm here. I throw the ball in front of me. There is some spin that I give it, right? There's a typical kind of trajectory. I chose it with very specific initial conditions, but it's just to illustrate one thing that can happen. Notice I throw the ball in front of me. That's the horizontal axis, right, this way. It bounces back, forward, back, but the net motion is back. I throw it that way, but the ball goes that way, right? On the other hand, this is three-dimensional. There's a floor. What you're seeing in the top picture is what you see the frontal image, right? Now, how about the depth, the other direction? So the horizontal axis for the lower graph is pointed that way. Notice that while the ball moved about, say, 15, 20 units of distance this way, it moved 150 that way. So it's all out there, right, in the math building. So this is not so surprising in the sense that we are all familiar with, if you play ping pong, right, you can give the ball a spin and it will play tricks with your adversary. But this is one thing that can happen. Here we see this could not possibly happen without a strong coupling between rotation and translation, right? So here the moment of inertia plays a very strong role. So let's do a few experiments in flatland, right? Dimension 2. Imagine we are all living in dimension 2. My walls are going to be the boundaries of some planar shape. And I need to explain one little thing here. How do we visualize what is going on, right? This system is, strictly speaking, well, so let me separate the trajectory of the center of the ball and the velocity. The center of ball will be described by the picture on the left. And notice again something that already indicates a kind of stability, right? Here we have a very long trajectory. It starts from the bottom of the triangle, hits the top, right, diagonal boundary component, bounces off the vertical side on the right, down to the horizontal base, up to the diagonal side, again to the vertical side, and then back, and repeats itself that way. On the right, I have the description of the velocities. So at every bounce, I look at the velocity. Remember, there are two components of the velocity in dimension 2, right? Two components of velocity for the center of the ball, and there is one component for the spinning. Here the ball is really a disk, right? Dimension 2. And the one component for the spinning. So three components for the velocity, two for translation on motion, and one for the spin. Because of energy is a quadratic form on those components, the velocity lives on a kind of a hemisphere. I flatten that hemisphere, I get a disk, and so the points on the disk on the right represent velocities. We don't need to worry too much about that. It's just that I'm going to use that picture to try to get a sense of how chaotic or not chaotic the system is. Yeah.
The graph on the left, that represents the path?
Yeah, exactly.
Okay, and the question I have, does it matter where the initial conditions, where it's launched from?
Well, I believe here, from any odd, I believe I started at the bottom, right? But it turns out that this is pretty much all that you see. Notice there is a kind of a tube here. The center of the tube is a perfectly periodic orbit. And all that you see in general for other initial conditions will be things of this type. Tubes around some kind of simple periodic trajectory.
So the pattern will persist
Absolutely.
across different initial conditions.
Absolutely. And we'll see dramatic cases of that in a few experiments. So don't worry too much about the picture on the right. We'll see its purpose in the examples that will come. So here's an interesting case. So imagine in dimension 2 you have the corner of the room. You throw the ball, or the disk in this case, right, against one side wall at the corner, so that it bounces the second bounce against the other side wall, right? You have a corner, possibly at different angles. The ball gets trapped in that corner. It doesn't go out. It keeps on bouncing. And here are very particular angles for which all the trajectories are periodic. And the period of the trajectory, the number of bounces before it returns to the initial condition will depend on the angle. But it's more or less, for a given angle, all the trajectories will be of this kind, with this slight modification of the shape, but the same period and the same look, right? Again, stability somehow, very different than the ordinary type that's generically chaotic. Yeah.
Is this for the theoretical ball or an actual ball?
No. This is the ideal ball. Of course, the real ball, the more you can approximate, the more you can make the coefficient of restitution close to 1, and the more you can make the ball rubbery to grip the surface, the more you approximate. Unfortunately, I couldn't show the little movie. You could see in that movie, after just a few bounces, similar phenomenon, right? So it's the ideal case, but it's not completely different from, at least to the extent that you don't lose too much energy, you can reproduce this kind of behavior, right? So here's now something to really test how chaotic it can be. You can see the shapes at the corners of this square. You can see shapes of billiard tables, right? On the top left, the famous Bonimovich Stadium billiard. Then top right, billiard with pockets, the mushroom billiard, the moon billiard. And all these examples for the standard billiard system, they are ergodic. But here is what we notice. I'm showing these velocity portraits, right, for several trajectories. You always see something like this. You have a sea of chaos. That's the random points in the background. But you always see some features, like these elliptic islands in the sea of chaos, right? You always see pattern, indicative of lack of ergodicity, right? Whenever you see these elliptic regions, islands in the picture, that is a sign that it's a region of stability that you did not destroy, right? So this, let me, another example of a similar kind. Imagine I have a polygonal table, right? In the standard billiard, if I give it a little curvature on the sides, I immediately make it highly chaotic. But in this case, I can never destroy these islands, elliptic islands. On the leftmost graph, all that we see is behavior of the type that we saw in the triangular example. These tubes around some periodic point. It's all over the place. As soon as we make the region a little bit concave, you begin to add some chaos in the background, but you never destroy the regions of stability. Right? So here's an interesting example. A disk with uniform mass distribution, an equilateral triangle. It doesn't matter the initial conditions. The ball will always return to you in a periodic fashion in no more than 6 steps. Right? It could not be more stable than that. Right? Circular table. I just want you to pay attention to this picture because it will have some significance in a few slides. On the left, I have the typical trajectory for a circular billiard table. In this standard case, you see the trajectory is forming a kind of caustic kind of circle in the middle, right? It's like these, string art, right? You connect pins with a string and you see these sorts of figures. For the Super Bowl, the ideal Super Bowl, you see 2 caustic circles in the middle. Keep that in mind. It's not of particular relevance just yet, but it will be.
Could you go back one slide? And my question is, there's no way to throw that ball that it would take more than 6 steps to get back to you? I wonder how did they prove that?
How did my student prove it? It's geometrically, absolutely. You can represent the collision map in a certain geometric way. It's all fairly concrete. Yeah, this is my student, Chris Cox, called this phenomenon persistent periodicity. And we don't know many other geometries that with the same effect. Note, if it's not uniform mass distribution, it wouldn't.
With any normal-sided figure, like a 5-sided or?
No. It's very special. Yeah. We looked for other geometries, but it's very peculiar, very special to the equilateral triangle, uniform mass distribution. If I change the moment of inertia, it will behave already differently. Right? So here's the no-slip Sinai billiard. The parameter eta has something to do with, it's a proxy for the moment of inertia. On here, the two sides, right and left, they have the same initial condition. I only change the moment of inertia. What you see on the left for a relatively small moment of inertia is a trajectory that looks very, very random. You do have very stable trajectories elsewhere. This one seems very chaotic. I turn the moment of inertia a little bit, and you already see the same initial condition gives something very, very stable. By the way, this is not a little different than the way that animation that you saw before. In that animation, the ball bounces off the sides of the square. Here, it's periodic boundary condition. You exit from one side and re-enter from the opposite side. But it's more or less the same story, right? And here is a velocity portrait with perhaps different values of the, I forget exactly what we did here, but different values of the moment of inertia, relatively small for the one on the right and relatively large for the one on the left. And this is a typical picture, even for something that wants to be, Sinai billiard, wants to be very chaotic, you never destroy these islands of stability. Yeah?
The island of stability, let's say I have some random trajectories outside of that. Once I'm in that zone, do I remain in that zone and I can't escape? Or is it, if I have 1,000 iterations, 700 of them are in there?
No, this is not ergodic, so you cannot go everywhere. So what will happen is, if you start your initial condition in that zone, it remains in that zone.
Okay.
It's a telltale of...
If I start outside, can I...
No, the outside and inside are invariant sets. And so ergodicity has to do with not having non-trivial invariant sets. So you have to go all over the place. Here, you start in that sea of chaos, you remain there, you cannot enter the zone of stability. The zone of stability is, I don't know, KAM, right? And like integrable systems, right? It behaves there like an integrable system. And it's an invariant set. If you're there, you cannot escape. If you're outside, you cannot go in, right? So with that in mind, I'll just formulate a conjecture that it's impossible to find ergodic no-slip billiards, right? We haven't found an example yet. We don't have a proof that it can't be, but it's a research question, right? Maybe one student will tackle it at some point. So in the few minutes I have left, let me say a few words about 3 dimensions, right? A few experiments in dimension 3. So here I'm looking at the side view of 2 planes, 2 walls, parallel walls. I throw the ball against one wall, it will bounce back and forth. Now there is gravity, right? Pointing down. The far left, gravity sets to 0. I chose the initial condition that makes it a periodic bounce back and forth. I turn the dial, increase the acceleration of gravity, but the ball never falls indefinitely. It remains in a bounded region on the height, the direction of the height, right? So, no falling. Again, there is a sticky quality to the motion of the ball. So no falling. We'll see a similar picture in just a moment. Let's look at a cylindrical wall. Imagine I'm playing the Super Bowl inside the smokestack, right, at the Washoe campus. I have this circular wall around me. I throw the ball and see what happens. If I'm sitting on top of the smokestack and look down, I see the same picture as for the disk in dimension 2. Now, okay, now there's a little subtlety here. The ball will fall, generally, but in a very peculiar way. Now I'm looking at the height function, right? For reasons, right, there's a purpose there. I threw the ball very close to the wall in a kind of a grazing motion, like a skipping motion, like you throw a stone on the surface of a lake, and you see the ball skipping in small steps, right, very close to the wall. And you see a peculiar motion. It is oscillating, right, the height. But if you look very closely, you see there is a little zigzag motion, a very small scale, that seems to be behaving as a kind of dissipative sort of component of the motion. The amplitude of the motion is decreasing, it's falling, accelerating down. But something interesting happens. If the transversal picture, you see two circles forming, these are caustic circles forming. If your initial condition is such that those two circles collapse to one, then the ball does not fall. Here, the dots in this graph are the heights of the ball at each bounce. Very closely spaced bounces. The line corresponds to the rolling motion. This, maybe I should explain, a very classical effect in mechanics. I wonder if you know about this. This goes back, I don't know, 19th century mechanics, non-holonomic mechanical systems. Suppose that I don't throw the ball against the wall, I roll it with a very fast speed. To the extent that it doesn't lose energy, it will never fall. It will move harmonically in the vertical direction. This is familiar to golfers and basketball players, right? There is this phenomenon in golf where you throw the ball, it gets into the hole, it feels like it's going down, but then it pops out again and leaves, right? It's this, or perhaps in basketball, the ball rotates on the rim, right, of the basket, feels like it's going in, but then it jumps out again. It's related to this effect. So this suggests that there is an affinity, a relationship between the bouncing of the super ball, the ideal super ball, and the rolling, the no-slip rolling, right? Again, we're assuming traction there that doesn't allow the ball to slip. But this example of the circular cylinder is too special to reveal this story. So let me finish with a very interesting insight that it's in the thesis of one of my students from a couple of years ago, which is the relationship between rolling and bouncing finally. That's the last point of the story that I want to tell you. These are very closely connected things, right? And the idea is that to understand the bouncing or to gain insight into the bouncing, it makes sense to go one dimension higher and look at the rolling. So let me try to explain what that means. Imagine that I have the billiard table for the Sinai billiard. It has periodic boundary conditions on the square sides. It has the circular scatterer, right? When the disc bounces off that circular scatterer, it reflects in a certain way. Now, let's think about a different system. I take that picture, put it in dimension 3, it's lying flat on the plane. I take a three-dimensional ball and allow it to roll on that plate. When it gets to the boundary of the scatterer, it's now a hole. It rolls over the edge to the other side. We don't care for now about any physical mechanism to produce that. It's just a mathematical connection that I want to point out, right? Allow me to assume that the ball is always in contact with the surface. It rolls, gets to the edge of the boundary of the table, rolls around to the other side. These two systems are the same, more or less. So the idea is that if the radius of the ball is very small, if you're looking from the top, you don't see the ball in it, right? You see the disc, you see the boundary. The behavior of the two systems will be essentially the same and become closer and closer together the smaller the ball is. So it turns out that we can think of the no slip, right? This rough or bouncing ball system as being a kind of a shadow of a three-dimensional phenomenon, like the Plato's metaphor of the cage, right? People trapped in a cage and something happening outside. They only see the shade on the wall of the cage, right? They're seeing part of the picture. So here there's a three-dimensional system that is nice from a mathematical point of view because it's governed by differential equations. It's easier to do analysis, a continuous system. But if you look from the top, you'll see the billiard ball, the bouncing ball, right? So here you may recall, let's see very quickly, so let's think about this example now as really two-dimensional. Imagine a strip, two lines, parallel perpendicular lines with gravity. It's a strip, the disk bouncing back and forth, right? What happens in the rolling system? It's more or less the same effect, but what is happening now is that we have a three-dimensional ball rolling on this strip. It turns the edge, right, every time it gets to the boundary lines. Under gravity, again, it's the same effect. You can see the slight curvature, right? In the bending, you see a smooth, it's not a sharp angle, right? You see the turning around, it's a smooth collision sort of effect. Finally, let me leave you with this example. This is the smokestack example, right? I have this circular cylindrical wall, but now I take that three-dimensional cylinder, I lay it flat in 4 dimensions. I step out of dimension 3, and look at my 4-dimensional ball rolling on top of that flat 3-dimensional cylinder. When it gets to the edge, now it's a 2-dimensional edge, right? It's a bit hard to imagine. The ball rolls around it. The picture on the right is the rolling on it's a kind of pancake surface where you can see, if you look closely at the angle at the end, there is a rounding, right? That is rounding into the 4th dimension and getting under this cross-section of the cylinder. On the right, you have the behavior of the height. And again, it doesn't fall if the condition of a single caustic line, right? Here we have examples of initial conditions where the 2 caustic lines collapse to 1. And in that case, you don't have falling. The motion, dimension 3, along the axis of the cylinder is bounded, is periodic, with some interesting features. And so I believe this is the one example of a result that is about ordinary Newtonian mechanics in dimension 3, where you go to dimension 4 to gain some insight into what is going on. With that, my time is up, so let me thank you for putting up with this.